Okay, continuing with chapter 3, we're going to talk about, go ahead and talk about remember the mass. The mass is equal to the number of protons plus the number of neutrons in each atom or the atoms within an element. So the mass is going to be listed in the periodic table for each of the elements. And this will become useful when you are trying to prepare your own solutions. So you want to dissolve a certain amount of solute in, let's say, water, and to create a solution. Now, you need to know this mass in order to calculate the number of molecules of your solvent that you need to put in this this solution that you desire, right? So the number of molecules of the solvent is equal to what's called the concentration. Often you will see concentration, or not really that term, but a number, right, inside these brackets right here. Now, the molecular mass of a molecule is going to be the sum of all the masses of the atoms in that molecule, right? So you'll get a practice calculating this, and I'll kind of talk about it on the next slide and allow you to do the calculation. However, a little bit further, we need to know what the concept of a mole is. So the number of molecules, which is typically measured in moles. Now, what's a mole, right? So a mole is just like a relative number equal to the number of molecules of any of the elements. It could be an ion, it could be even a molecule, right? An entire or a compound. So 1 mole is equal to what's called Avogadro's number. It's 6.02 times 10 to the 23 molecules. And again, it could be molecules, ions, compounds. It could be the entire compound that we're talking about. And you'll see an example on the next slide. Now, Avogadro's number, or Dalton, so another term for Dalton or mass, let's say, or atomic mass units, which would be just the same as the atomic mass that's listed in the periodic table, is equal to 1 gram, right? So we can say that instead of using 6.02 times 10 to the 23 molecules, we could say that 6.02 times 10 to the 23 molecules, or Daltons, is equal to 1 gram. Now, going back to the concept of a concentration. So concentration, again, is the solute, the number of solute molecules that are in the entire solution. One term used to describe concentration is called molarity, and that's using the capital M in italics. Molarity is the number of moles of solute. So here we're talking about number of moles in solute, okay, in a liter of solution. That's a concentration. So I want you to try to calculate how many grams of each of these solutions. So remember, 1 gram is equal to 6.02 times 10 to the 23 molecules. So you don't have to use that right there, but you can kind of relate it to the mass that's listed in the periodic table. Hint, a 1 molar solution is equal to 1 mole of sodium chloride. A 1 molar solution of sodium, or 2 molar solution of sodium chloride would be equal to 2 moles of sodium chloride, and a 1 molar solution of, this is glucose, C6H12O6, is equal to 1 mole of this entire thing. So remember, you need to calculate basically add up all the masses of each of the atoms that are in these molecules in order to determine how much in grams that 1 mole of each would be equal to. All right, so you go ahead and try those calculations, and then I have a separate file with the answers. So I showed you the calculation and I described it as I go through. If you are totally stuck, you're more than welcome to jump over to the video of the calculation and take a look. So it's important to know that water is always in a state of dynamic equilibrium, and it's in equilibrium between these molecules right here. So remember, we have the reactants and the products. Here we have two water molecules in equilibrium with a hydronium ion and a hydroxide ion. So you can see the hydroxide ion is missing a hydrogen. The hydronium ion has an extra hydrogen. So changes in concentrations of the hydronium ion or the proton, right? So you have an extra proton attached to this water molecule, which makes the hydronium ion. And the hydroxide ion can affect the chemistry of the cell. What this does is change the pH. So on the next slide, I'm going to show you the transfer of hydrogen between these molecules. Systems can be affected by acidic and basic conditions. Acidic conditions and basic conditions can change when there's transfers of hydrogen between molecules, and this can happen within water as well. So let's go ahead and take a look at the transfer of a hydrogen between two water molecules. So I'm going to go ahead and draw two water molecules. We're going to draw them so that they are in a hydrogen bond with one another. So this is partially negative here. So we'll go ahead and draw a dotted line. And then we have the positive side of another water molecule interacting with the negative side of the one that we initially drew. So this is the positive side. Okay, so we've got a hydrogen bond here. Now, let's say this water molecule loses this hydrogen right here. So what happens when a water molecule loses that hydrogen? Let's go ahead and take a look. So if we draw this like this again, we have the hydrogen, and then we just basically draw the electrons right there. Okay, so let's just say the electrons are still there, and the hydrogen is basically given off as a proton. Okay, what a proton is a positively charged hydrogen ion, right? So what happens is it basically leaves behind that electron. Okay, so what's left is another ion. So now we have a negatively charged ion. Okay, so we've got this, and this has got extra electrons right here. Okay, this is a hydroxide ion. Okay, so this proton can just sit in solution, or it can be combined with another water molecule. So when it becomes combined with another water molecule, so let's say we're inputting this hydrogen ion, okay, then we end up with this right here. Whoops. Okay, so this is going to be positively charged. This is actually written like this, H3O plus, it's positively charged because it has an extra proton. Okay, this is the hydronium ion. Okay, so now we have hydroxide ions and hydronium ions. So when there are hydronium ions, when there's an excess amount of hydronium ions, the solution is going to be more acidic because it's got extra hydrogen ions in that solution. And then if a solution has excess hydroxide ions, in any solution in which water is the solvent, at 25 degrees, the product of the protons and the hydroxide ions is always constant. So it can be written like this. So remember, we've got the concentration of the hydrogen ions, and the concentration of hydroxide ions is always equal to 10 to the minus 14, and usually that's in molar. The pH of a solution is defined by the negative logarithm of the hydrogen ion concentration is written as ranges from 0 to 14, and right in the middle at 7, that's a neutral solution. So anything below 7 is going to be acidic. Anything above 7 is going to be basic. So at neutral pH, the concentration of the hydrogen ions and the hydroxide ions are equal. In a solution that has a pH that's below 7, the concentration of the hydrogen ions is greater than the hydroxide ions. So there's more hydrogen ions in that solution. And in a solution that has a pH above 7 has a greater amount of hydroxide ions in terms of concentration than the hydrogen ions. And these are some common examples of solutions and their relative acidity and basicity. Now, a basic solution can also be called what's called alkaline. Okay, so alkaline solutions are basic solutions, and both of them are going to have a higher amount of hydroxide ions than hydrogen ions in the solution. Related to pH, it's kind of important. If you went back to the pH scale, you'll see that blood is about neutral. Not quite. But the internal pH of living cells is typically about neutral, but in some tissues it might be more acidic or more basic. For instance, our stomach is more acidic and our intestines are going to be more basic. Now, to maintain these pHs, the solution is made up of what's called a buffer. Okay, so buffers help maintain the pH at the pH that it's supposed to be. So whether that be pH 7, whether that be pH 2, whether that be pH 10, it's meant to help keep a constant pH. If the pH changes in living system, that could be detrimental. So in the blood, and it involves the lungs, a transfer between the carbon dioxide and oxygen in the lungs, this helps maintain the buffer system in the blood, right? So this is called the carbonic acid bicarbonate buffer system. And there's an equilibrium between carbonic acid and bicarbonate in the buffer system with a reserve to adjust for any changes in pH that may occur. I'm not going to get into too much specifics about this. This will be covered perhaps in another course, for instance, biochemistry or even anatomy and physiology. So in summary, I talked about solutions and kind of talked about the basics. You'll do some sample calculations. You'll be able to see my video, what a concentration is, and then what pH, how to calculate the pH and the pH scale, and what is a buffer. Thank you for listening.